Good morning or good afternoon. My name is Professor Duke Orata. We are continuing with our thermodynamics lectures. Last time we talked about condensation on a vertical wall, and these were processes which involving phase transformations. So we're just continuing to look at even the condensation patterns today. But first of all, we need to mention that when we look at that wall, remember we had our wall. This y, that was x. That was sigma. This liquid film. The condensate M plus dm, condensate. We had our velocity profile. And we had looked at this element, or dm, so I. Now, we developed expressions involving this vertical wall. We know that the thickness is 0 at the top of the wall, and we were able to come up with the expression for the Nusselt value over the x section Remember, we had that, and I kindly continue urging you to look at our lectures so that we move systematically together with these things. And we have seen that the Nusselt, for that section X, we had seen that we had the enthalpy, we had the acceleration due to gravity, that is the density, that's the segment dimension there, that was the temperature, that was the dynamic viscosity, that's the thermoconductivity, all this fourth root of that. And these quantities are dimensionless. These quantities are dimensionless. This quantity is dimensionless. And that was the Nusselt value. The Nusselt value over the x section. Now, normally we talk of average values. So we need to think of the average value of the average value of the heat transfer coefficient over that segment, let's say, over segment L. The average value of H. It's very important normally to have the average value, and that is over a whole segment. Let us call it L. Let us say that that segment is L. So the average value of heat transfer coefficient for segment L is very important because you need to get mean values of some of these things. We saw this mean, we talked about mean velocities when we were dealing with the turbulent flows and so forth. And mean value is a good estimation of things. So if you look at heat transfer coefficient, that is H, heat transfer coefficient H, its mean value, assuming that the value of H, some distance L down the wall is HL. assuming the value of h some distance L down the wall is HL. So if you assume that the value of H, some distance L down the wall, remember we're still talking about the same profile, which you have done repeatedly in several lectures, and now you're familiar with it, then in that particular case, the average value of the heat transfer coefficient will therefore be given by H will be equal to L integral, and this will be 4/3 HL. And so in the same way, the same will be true for the Nusselt value very important for us to note that particular quantity. Now, suppose you are thinking of a cylinder with diameter D. You're trying to compute the heat transfer coefficient value for a cylinder with dimension D. The process is just the same. Just remember when we did with the heat transfer in an annulus and in pipes, you just look at those lectures and you see how we took the dimensions in terms which we worked with there. And so the process is still basically the same. So what we are saying is that for a cylinder of diameter D, the heat transfer coefficient H for that cylinder, for that particular cylinder, will be the same as that of the vertical plate, but multiplied by a factor. So for a cylinder diameter D, the heat transfer coefficient will be similar to that of a vertical plate, where similar to that of a vertical plate, where D is equals to 2.85, where L is equals to 2.85 D. So the length of that vertical plate will be 2.85 times the diameter. So when you're dealing with a cylindrical pipe, its heat transfer coefficient will basically be the same as that of a vertical plate whose length is L is 2.85 times D. So that's a very important thing to note. And therefore, if you express in terms of Nusselt factor or number, then the Nusselt number for this cylindrical unit whose diameter is D will just be the same, just multiply by a small factor to separate out things. Not forgetting that's the enthalpy change. We talked about that enthalpy change when we have the condensation process. That's the enthalpy change, remember. And G is acceleration due to gravity. We have rho, that's the density, and that is the diameter of the pipe. And theta is that temperature difference. And mu is dynamic viscosity, and K is thermal conductivity. So basically these quantities have their similar values, so we just say lowest density, just in case. That is enthalpy change, mu, dynamic viscosity, theta is temperature change, K remember, is thermoconductivity. What are we missing out here again? So we have basically G is acceleration. You are familiar with that. Now, the rate of condensation is normally can be high, can be low. And several factors can cause this. So let's look at factors affecting rate of condensation. So factors affecting rate of condensation. Now, there are several factors which can affect the rate of condensation. One of them is the velocity of the vapor. Velocity of the vapor. So if the velocity of vapor is high, the vapor is moving very fast, then what will happen is the drag on the film, on the liquid film, will reduce the thickness of that film. And when it reduces the thickness of that film, of course, there will be an increase in the conductivity, the rate of conductivity, heat conductivity. When the velocity is high, there will be greater drag. On the film, liquid film, resulting in a decrease in sigma. And so when they start decreasing sigma, of course, the rate of heat conduction, the rate of heat transfer will increase. Heat transfer. The second possible cause for this, the second possible cause for change in the expectations with respect to the rate of condensation can be a case where as the fluid flows downwards, it reaches a critical value above which now we start developing ripples and turbulence in the system. And like we have already seen severally, we have already seen, for example, that there is a value, Reynolds number, above which or below which we can expect turbulence. We said in the pipes it was around 2300 in terms of Reynolds number. Remember Reynolds number, don't forget Reynolds number. Reynolds number Reynolds number was, that was Reynolds number. Don't forget that. And we said that it's a certain value. It's a certain value, that's the dimension. It's a certain value, a critical value, above which you will now start developing turbulence. So we believe that even when this fluid is flowing down, Well, it reaches a point where it reaches that critical value where we start developing turbulence in the system. And that is given by Reynolds number for fumes is thought to be 4m over mu. The critical number for a film. That critical Reynolds number is thought to be related to the rate of condensation and the dynamic viscosity there. So, in a nutshell, what are we saying? Let's just say, write it down. We are saying that when the fluid is flowing down the wall, the plate, a critical point is reached, beyond which we develop turbulence in the system. And we think this corresponds to Reynolds number for fumes of 4m over mu. The other thing which is there is the pattern of condensation. The pattern of condensation, especially when the fluid is water vapor, for example. The pattern of condensation. The pattern of condensation. Case of water vapor. Now, when you condense clean steam on a clean surface, we expect film-wise condensation. Film-wise condensation. In other words, you expect the condensation, you should develop a film. That is if you have clean steam and a clean surface. For the case of clean steam condensing on a clean surface, we expect film-wise condensation. In other words, you'll form a film. But there are occasions when you probably have impurities in the steam or on the surface. For example, you can have organic compounds such as fatty acids, or you can have oil. You can have some of those organic materials. In that particular case, you will have dropwise condensation. When the steam or surface has impurities such as oil or fatty acids, then we'll have dropwise condensation. So you form drops. Remember, for example, when you have an organic material, it's hydrophobic. It doesn't love water at all. Note, organic materials are hydrophobic. In a nutshell, they hate water. They hate water. And so it will not mix with water. So there will be separation. So you don't expect that uniformity associated with a film. In other words, if you take, for example, that impurity as an hydrophobic and an hydrophilic end, this is water-loving end, and it has an hydrophobic tail, that's water hating, hates water,